Hello everyone, my name is JArnold, and I've been working with graduate student Jordan Chapman and Professor Chera Saladino on enzyme immobilization within a hyaluronic acid matrix for biosensor applications. First, I'm going to go into a little description of the key components of this project to put everything into a bit of perspective for you all. Enzymes are proteins that help to encourage certain reactions to take place in a shorter amount of time. These reactions are essentially what run the biological world as we know it. And there are two key pathways that enzymes can take. They can either take larger molecules and break them down into smaller components, or build these smaller components up into larger molecules. For example, when you digest your foods, these carbohydrates, lipids, and proteins that you eat are going to be converted by enzymes into heat, energy, and cellular building blocks. And then from there, these nutrients are going to be built back up into the macromolecules that make up who it is that you are. Using enzymes as opposed to chemical catalysts is more biocompatible, biodegradable, highly selective, and reusable, just to name a few advantages. And there are a lot of applications in which these biocatalysts are used to optimize a desired reaction. Just to name a few, these include the medical, biofuel, waste management, and food and material production and preservation industries. But again, enzymes are ubiquitous within the society that you know and love, making research in this area incredibly relevant. Now, the way that enzymes quicken up these reaction processes is by decreasing the amount of energy that you need to invest within that system in order for a reaction to occur. To show this, I'm going to show you the effect that our model enzyme, glucose oxidase, has on the reaction of beta-D-glucose and oxygen to form D-glucano-delta-lactone and hydrogen peroxide. Without an enzyme involved, you can see that it can be very difficult for the two reactants to acquire enough energy to reach the point of reaction. While these reactants can react on their own in nature, it's much slower than in the process of a catalyst because of that necessary level of energy input. Now, as you can see here, when glucose oxidase comes in the mix, a much more efficient pathway can be taken in the formation of our wanted products, thus making the reaction more easily facilitated and faster. As mentioned previously, enzymes are biological units that come from nature, and if we want to use them to increase the efficiency of reactions within scientific and technological innovation, then these peptide systems must be removed from their natural state and placed within new synthetic environments. While enzymes are incredibly useful when they work properly, they do have the limitation of being susceptible to denaturing when exposed to temperatures and acidities that they weren't naturally intended to work at, thus making them incapable of carrying out their reaction. An approach to this issue is enzyme immobilization, wherein these biocatalysts are placed in synthetic microenvironments in which more optimal conditions can be maintained while the enzyme is still able to have access to its corresponding substrates and able to release its desired products, otherwise known as activity maintenance. Additionally, immobilization onto or within a platform enables more user controllability than, say, a free-floating enzyme within a solution, and allows for qualities such as reusability of the enzyme. This figure here represents a few of the key means of enzyme immobilization. First, we have encapsulation, where enzymes are placed within capsule-like structures or particles. Then there is physical adsorption, where the enzymes are essentially stuck to a surface. Entrapment is a method that I will be using in my research, which is where you have kind of a net or web-like matrix that catches the enzyme within it. You can also have chemical bonding. So here is ionic bonding, where the enzymes and the surface are oppositely charged and attract one another. You can also have covalent bonding, which is stronger than ionic and involves the sharing of electrons between the enzyme and the surface. And lastly, there is cross-linking, where the enzymes are chemically bound to one another, and that enables a matrix that's a lot more easily manipulated by researchers than just having the individual enzymes. If the next generation of enzyme-viable immobilization platforms are to be considered for extended medical applications, one has to aim for integration of biocompatibility, lubricity, and hydrophilicity characteristics, along with bioactivity to enable improved stability and activity of a given enzyme-based platform. So that's where hyaluronic acid comes in. HA is a disaccharide that occurs naturally between the cells of nearly any given living organism. It's what gives you that hydration and lubrication in your eyes, joints, and skin. You may have heard of it in a lot of commercials for serums and creams recently because it has these moisture and anti-aging properties. Its viscoelastic, motility, and moisture-retaining properties also lend it anti-inflammatory, tissue regenerative, and cellular signaling capabilities. All of these things mean that HA is biocompatible and hydrophilic, just like that desired enzyme immobilization platform should be. And it can be applicable in biosensing, like in this glucose sensor, diagnostics, and drug delivery, especially for targeted delivery of anti-cancer drugs due to its CD44 receptor, bioimaging, tissue engineering, and wound healing, among many other areas of biomedical engineering. The goal of this research is to design an enzyme-based biocompatible biosensor with real-time tracking capability. To achieve this goal, our hypothesis is that biofunctional polymers, such as HA, and alkylamines, including dodecylamine, hexylamine, and octadecylamine, could be isolated and manipulated to serve as support unit for enzyme-based technologies, in this case being a glucose sensor. Now, as you can see in this concept figure, my project entails the cross-linking of differing ratios of HA and these alkylamines to form hydrogels of corresponding porosities through 1-ethyl-3,3-dimethyl aminopropylcarbodiamide reaction chemistry. Next, we will be implementing an enzyme immobilization procedure in which the test enzyme, glucose oxidase, will be loaded into or onto these hydrogel samples. The differing pore sizes will result in various loading phenomena, as larger pore sizes will cause less enzyme to be caught within the gel, yet the larger pore size also generally corresponds to greater enzymatic activity, as the enzyme has greater contact with the substrate-filled solution. Therefore, there is a Goldilocks zone of sorts that we will need to determine. Finally, I will be applying these gels to a functionalized gold electrode, where I will test the applicability of the resulting biosensor in terms of continuous, real-time, cost-efficient, and sensitive glucose sensing. In an application like the one I'm presenting today, the goal is to create a system that can utilize the work of enzymes to their utmost potential. And to do this, we're going to have to optimize the process of the creation of our systems, the immobilization technology that we choose, and the enzyme itself. And the hypothesis is that by user controlling the porosity and stability of an HA network, a maximized enzyme loading and activity of the immobilized enzyme can be achieved. And in doing so, in conjunction with the gold electrode for electrochemical signal detection, a sensitive and specific biosensor can be formed. While I have been working on this project for the last 3 years, unfortunately, limitations regarding lab time over the past year have slowed the development of gaining results as far as how well these hydrogels perform, as we've just begun producing samples again this summer. However, some work was done previously in learning the basics of testing these hydrogels for enzyme loading and activity. In the BCA assay process, a color change is observed upon incubation of the gels, as well as a series of serial dilutions of known enzyme concentrations. This color change corresponds to the amount of enzyme within a given sample, which can be detected as light absorbance with a spectrophotometer, meaning we can find the enzyme concentration based off where the hydrogel's light absorbance falls on a standard curve. Through this analysis of a 1-to-1 HA to dodecylamine ratio, it was found that on average about 0.055 milligrams of the 0.125 introduced to the hydrogel were successfully immobilized. Now, there are several problems that could be faced in the future. For example, it's possible that the enzymes loaded onto the gel don't show very high activity, as the substrate could have difficulty reaching the enzyme to react because of that surrounding matrix. However, by adding additional cross-linking steps, or changing the porosity of the gel, this can be combated to allow for easier access of the substrate and easier release of the product. It is also possible that the enzymes don't have an improved stability in those acidities and temperatures that we need them to work at. And this can be approached by trying to cross-link polymeric aldehydes to the enzymes before immobilization to provide them with more strength and protection. Lastly, future work may require the assessment of a low biosensor sensitivity, meaning the produced glucose sensor would not be able to clearly detect low concentrations of sugar. Here, the approach would be to add more enzymes to the gel on the same area, providing more places for substrates to bind and eventually be sensed, thus enabling a greater electrochemical signal in the same low analyte concentration. Finally, I want to acknowledge and thank the National Science Foundation, the WVU Statler College of Engineering and Mineral Resources, and the Arnold and Mabel Beckman Foundation for their support not only of myself and my research group, but of all those working towards scientific discovery. That's all I have for you today. Thank you so much for listening, and I would be happy to answer any questions.